Hello, class. Unfortunately, unbeknownst to me, the right when I was starting I sub R1 in the other fashion, um, the recorder, whatever, the computer, something on there cut out. And so you were unable to see where I went and how I figured this out in the second way. So that's what I want to do is I want to go through from here on down and point out what I did. Now, the first thing that I did, of course, up here was I just took the voltage across that impedance branch, right? Because this one is 110 volts up here, 110.2 volts up here, and then that 0 volts at 0 degrees down here. So I knew that that was the voltage difference. And then I also knew that this branch of the circuit had a resistor and an inductor that had a together impedance, combined impedance of 141 at 45. And of course, that's how I got this. And everybody was here when I did that. Then when I did the I sub R1, I did it a different way. I said, okay, well, here's the total current that's flowing into node A, right? Here's the current flowing into node A. And then the current that's flowing out of node A, if I wanted to find out what's going down this one, I would take the inverse lever rule, right, that I taught you, which is to take the impedance of this part of the circuit. So I'm taking the impedance of this part of the circuit over here in my numerator. That's the 353.6 ohms at 8.1 degrees. And where did that come from? That 353.6 ohms is 350 plus, it's in the last lecture, but it's 350 plus J50, I'll write it down here, ohms, right? 350 plus J50, and if you're working out, the phasor is 353.6 at an angle of 8.1 degrees. And then on bottom, what I did was I added both of these together. So 350 plus J50 added to the 100 plus J100, which is here, right? So we add up what's in both of the two parallel circuits that we've got here on the bottom, and that's what I get, 450 plus J150, and that comes out as a phasor to 474 ohms at 18.43 degrees. Now, when I divide these two, that again came out to the 0.78 amps peak, just like I hoped that it would, because now that I know that these two totally different ways of solving for the current in this branch of the circuit have given me exactly the same answer. So that tells me that I've done it all right up to that point. Now, the next thing that I wanted to do was I just wanted to find out, well, what's the current? Because I've got to find the voltage at B too, don't I? And so I just wanted to find out, well, what is the current through R2? So I can find out what the voltage drop is across R2, and I can find the voltage at B, right? Because that's what I want to do. So I said, well, okay, well, I sub R2, the current that's flowing through here, because if this current's flowing into the node at A, then the current can only be flowing out down here, and it can be flowing out over here, right? And we know what the current is flowing down through here. That's 0.78 amps peak at 14.7 degrees. So if I subtract that off the total current, then that, and this is the total current, the 105 or 1.05 amps at 25 degrees. I've just broken it down into its rectilinear form, and I have it over here. We did it when we first started that last lecture too. So I have that, and then I've just subtracted off this in its rectilinear form, which we already did in the lecture right before this. You've got that in your notes, so I'm just subtracting that off. And what that gives me is this in rectilinear form, 0.198 plus J 0.246 amps peak, right? That's just subtracting 0.95 minus 0.754 and 0.44 minus 0.198, and that gives me 0.198. That's odd, isn't it? How that? Anyway, it's a coincidence, I'm sure. plus J 0.246. And that gives me a current that we see there of 0.3, I'm just going to circle it, 0.3, there's a point, 0.315 amps peak at 51 degrees. So that's the current that's flowing through R2. So we can now figure out what the voltage drop is across R2. Because we know the current flowing through R2, we know what the value of R2 is, 200 ohms at 0 degrees. So if we multiply those two things together, we find out that the voltage drop, not the voltage at B, but the voltage drop from A to B is going to be 63 volts at 51.1 degrees, and in rectilinear form, 39.56 plus J, 49 volts. So let's find the voltage at B, right? The voltage at B is just going to be the voltage at A, which we know here is 110 volts at 59.7 degrees, or 55.6 plus J, 95.2 volts. I should probably put volts there, since I tell you guys I always put your units on things. Okay, so I did that. 55.6 plus J 95.2 minus 39.56 plus J 49 volts, and I get 16.04 plus J 46.2 volts. When I turn that into a phasor, I get 48.9 volts at 70.85 degrees. So there you go. I just did this little thing over here too at the end of it. I wanted to show you how if you had a complex fraction, if you multiply the complex fraction by the complex conjugate, which means you just change the sign, right? Then you can do that, and you get a new number. It's down here. I don't think you can see it. That is a non-fractional. It's still a complex number, but it's not in fractional form anymore. I just thought I'd show you that. Okay. Well, there you go. And I'm not going to stare up here and not see anything this time like I did the last time. I was like, hey, what's going on here? It's like my computer shut down or something. Or maybe I had like no power left. And now you can't even see the little arrow thing. Come on, give me an arrow here. I'll get there. There we go.